I go ahead with the syllabus, I just want to, for a minute, take you to Coulomb's law in the vector form. I hope I am audible. You cannot hear me, I guess. Can you hear me?
Yes, ma'am.
Okay, so I'll just take you
Yes,
through
ma'am.
Coulomb's law in the vector form once. So here in the figure, you have two charges, Q1 and Q2. Please, the first thing that you should remember is that Coulomb's law in this form is valid only when the charges are particles, not extended objects. Okay, that's the first thing you have to remember. And next thing is, then let's just look at this equation. I have two charges Q1 and Q2, and I'm talking about what is happening to one because of two. What is happening to 1 because of 2. So I am bothered about the position of 1 with respect to 2. So the position of 1 with respect to 2 is vector R1, 2. Okay, and let me look at the force. If both of them have the same sign, you know that there is going to be a repulsion. Okay, so if I repelling means what? Q1 trying to move away from Q2. So F12 gives you the direction. Okay, now what you do is write the equation for F12 using Coulomb's law. It is 1 by 4 pi epsilon naught Q1 Q2 by R12 square, and the direction is the same as R12 vector. The direction is the same as R12 vector. F12 and R12 are parallel to each other. Okay, but then that should be seen in the equation. So what we do here is we give the direction. This is the magnitude, okay, and this is the direction. So how do we give the direction? You know what is I cap, j cap, k cap. I cap is a unit vector along the x direction. Similarly here, R12 cap is actually R12 vector divided by modulus of R12 vector, or it is a unit vector parallel to R12. R12 direction is this arrow. Therefore, my F12 is parallel to R12. If you understand this logic, okay, you will be able to understand what we are going to do from now. Next thing is, you must have noticed that I am using Q1 and Q2 modulus Q1, modulus Q2. The reason why we are doing that is, whatever be the sign of the charge, if I'm talking about a minus 3 nanocoulomb and a plus 2 nanocoulomb, when you multiply, don't take that minus into account. Just say 3 into 2. Just take it as 3 into 2. But then where does the sign come into picture? The sign, whether it is a repulsive force or an attractive force, will figure the minute I'm going to write this. When I put this, it is taken care of. So don't try to multiply the charges with their sign. Leave aside the sign. Whether it is repulsive or attractive will be taken care of by writing this. If it's an attractive force, what happens is there will be a minus sign here. Okay, like here you see, there is a minus sign. That means F12 is anti-parallel to R12. Then there is a minus sign here. So this is an attractive force. A repulsive force will not have that minus. Okay, with this in mind, let us just go ahead with the syllabus. Okay, now we can't be always talking about point charges. We will have to talk about situations where we don't have point charges. Like for example, I have an extended object like this, which is, let's say, positive charge, and let's say it's carrying a charge Q. And I'm talking about a point charge Q naught. I want to talk about what is the effect of this Q on Q naught. What is the effect of Q on Q naught? I cannot write this equation, Coulomb's law, 1 by 4 pi epsilon naught Q by R square. No, I cannot do it. It is applicable only for point charges. So for extended charged objects, you cannot use that equation. So what do you do then? You have to use the method of calculus. Okay, you have to use the method of calculus. You will have to differentiate. You have to actually divide this object, this big object. You have to divide it into a number of small elements. You have to divide it into some number of small convenient elements. Okay, so small that each of them carries a charge dq. When I say d here, I'm talking of a differential element, a small charge dq. And it should be so small that it can be treated as a point charge. It should be so small that it can be treated as a point charge. Now what you do is find out where is dq with respect to, where is dq with respect to your q naught. Okay, let's say this is my Q naught and this is the dq that I've taken. So let me just connect these two and say that Q naught with respect to Q dq is at some R. Okay, next I have to do the same for each of these elements. I have to do the same for each of these elements and then apply the principle of superposition. Okay, and add up everything and add up everything. And when I do that, what happens is if I take 10 elements and add up, it is a summation. Instead of 10, if I am going to have, let's say, a million elements, and if I have to add them, then it is no longer a summation. A summation becomes an integration. A summation becomes an integration. So this is what is the philosophy of taking care of continuous charge distribution. So let's quickly see what we do. We divide the net charge Q into infinitesimal small elements dq. That's what I just told you. And dq should be so small that dq can be treated as a point charge. And because this charge dq is very small, let the force be also very small. Let the force be df. Okay, so let's write the equation for df. Df will be, so here whenever I'm writing k stands for 1 by 4 pi epsilon naught. Okay, I'm just doing this because I don't want to again and again write 1 by 4 pi epsilon naught. So df is the force on q naught because of the small element dq. Therefore, it becomes k into q naught dq by r square, and the direction is some r cap. Is the step clear to you?
Yes, ma'am.
Yes. Right. Now what you do is do the same for all the elements there. And I have to somehow connect all these DQs. I have to connect all these DQs to the geometry of the material. So what I have to next do is I have to express DQ in terms of charge distribution and size, that is geometry. I have to connect DQ to the size of the element. I can do that by doing it via the charge distribution. What it means, I will just explain in a few minutes. Next, what do? I have to get the net charge. If I have to get the net charge, what I will do is I will write the equation for F. Sorry, I will write that my F is going to be simply integral df. I get df for each element and then integrate it. And when I do the integration, what I should do is I should look for geometric symmetry. If there is a geometric symmetry, what will happen is certain components of the forces can get cancelled out and it will be easy for me to do the integration. Okay, so what we will do in this chapter is we will take specifically 3 charge distributions which have some symmetry and then see how to apply this method of calculus. So I told you just a minute back, I said we will talk about dq in terms of, anyone remembers? In terms of charge distribution. I use the word dq in terms of charge distribution and size of element. The size of the element that I am taking. So what we'll do here is let us see what are the different types of charge distributions that can be there. One can be if my mass is a line mass. If the charged object Q is one line, it's one dimensional. Then the charge is along a line. The charge distribution is along a line. And I'm going to assume that if I have 10 Coulomb charge, all the 10 are uniformly distributed along this line object. Okay, then I can talk about what is called linear charge density. Linear charge density is denoted by the symbol lambda, and lambda is equal to the total charge Q on the object divided by the length of the object. Divided by the length of the object. If it is a uniform charge distribution, the linear charge density is the total charge of the object divided by the length of the object. And what will be the unit, anyone? Linear charge density unit will be, Q will be Coulomb and length will be meter. Therefore, it will be Coulomb per meter. Okay, so this is the charge distribution. Now I have to write dq in terms of this. So let us say that I have an object which is lying along the x-axis and I take a small, let the length of this object be n. Let the total charge be q. So lambda is q by L. Now I take a small element dx. I take a small element dx and I want to know how much is the charge dq on it. So what do I do? How do I do? I know cost of 10 pence. I want the cost of 2 pence. So what do? I find the cost of 1 pen and multiply it by 2. Yes or no? I know the cost of 10 pence. Each pen costs something. So I know the total cost of 10 pence. Okay. I want to know the cost of 2 pence. So what is the first thing I will do? I will get the cost of 1 pen. That is your lambda. And then I want the cost of 2 pence. So that will be dq. And 2 is like your dx. Okay. Therefore, I will simply say that my dq, the charge present in dx is dq is equal to lambda into dx. Cost of 1 pen into the number of pens. Okay, that's the logic. Similarly, I may be talking about a two-dimensional object, of area A, okay, carrying a total charge Q, and let us say that the charge distribution is uniform over the surface. Now, I divide it into a number of small elements and take one element of area dA carrying a charge dQ. Okay, now here the charge distribution that we are talking is going to be surface charge distribution. Surface charge distribution is denoted by the symbol sigma, and it is going to be, anyone can say, it will be surface charge distribution. Therefore, it will be total charge divided by
area,
area. And the unit will be
Coulomb per meter square.
Coulomb per meter square. Okay. Now I want to know how much charge is there in that area element dA. It is dq. So I can get dq in terms of the charge distribution. It is sigma into dA. Again, cost of 10 pence, cost of 1 pen, cost of 2 pence. Okay. Now, next, let us go to a three-dimensional object. Let us say I have a three-dimensional object like this of volume V carrying a charge Q. So now, what will be my charge distribution? It will be a volume charge distribution. Again, I'm going to assume it is uniformly distributed. Okay, so what do? I say that my volume charge density is rho. It is going to be given by, anyone can say, rho will be, follow the same logic,
Q by V,
Q by V. And what will be the unit?
Coulomb
Coulomb
per
per
meter cube.
meter cube. Okay, now I want to know how much of charge is there in a volume element dV. Let that charge be dq. So I can write dq is equal to rho into dV. So you should just understand these things. That's all. Once you get a hang of it, then we will use this for extended charge objects. Okay, so always we go from the simple to the complex. So we start off with the simplest. The simplest discussion would be on a uniform line charge. It's a uniform line charge of total length L. Okay, and let the total charge on it be some Q. Let the total charge be Q. And let the length of the element be L. Let the length of the entire charge object be L. So immediately you can tell me what is going to be my lambda. So lambda is going to be Q by L. Next thing is we want symmetry. Okay, and before that I will tell you what we intend to find out. We intend to take the perpendicular bisector of this line charge and call that axis as the y-axis, call the midpoint as the origin, call this axis as the z-axis, okay, and on the y-axis, at a distance y, we place a point charge q naught. We put a point charge q naught and we want to know what is the force on q naught because of q. What is the force on q naught because of q? Okay. So now we have to look for symmetry in this problem. So what we will do is we will choose the origin in such a way that it is at the center. It is at the midpoint of this line charge. It is at the midpoint of this line charge, and this line charge extends from minus L by 2 to plus L by 2 so that the total length is L and the origin is exactly halfway. And now I am taking my y-axis, and on the y-axis I place my charge q naught. Okay, and I want to find out what is the force on q naught. Okay, so what I will do is we have to use the method of calculus. So first what we will do is at a distance z from the origin, at a distance z from the origin, we take a small length element. We take a small length element of length dz carrying a charge dq. So immediately you can tell me how to write dq in terms of dz. dq will be equal to, in terms of dz, how will I write dq?
Lambda into
Lambda into dz. Yes, thank you. So dq is equal to lambda into dz. We have done that. Okay. Next, what do? You have to write the expression for df. We have to talk about, first of all, where is this located? It is located at a distance r from q naught. The distance between df and q naught is r. And let's assume dq is so small that it is like a point charge. So now let us write the equation for df. Let that force be df. I will write it as 1 by 4 pi epsilon naught. Then I will write q naught into dq divided by r square. Okay. Now instead of dq, I can put lambda into dz. Okay. I do that. Then after writing that, I don't want some unknown variable r there. So what I will do is, from Pythagoras theorem, I know that r square is equal to z square plus y square. So I just make that substitution here. It is z square plus y square. Next, I don't want to write 1 by 4 by epsilon naught. I am lazy. I am going to write only k there. And you must note that I am putting modulus there. And my force is a vector. I have to give a direction to my df vector. Let's assume that Q naught is positive and the line charge is also positive. Let both of them be positive. So what will be the direction of df then? And please draw the arrow on Q naught because you are talking about what Q naught is going to experience. Okay, so you have to put the arrow on Q naught. Will it be a repulsive force or attractive force? Will it be repulsive or attractive?
repulsive.
Repulsive. So you have to draw an arrow starting from Q naught along the line joining the two charges and away. That's repulsion. That is Q naught is going to be pushed away. It's going to experience a repulsive force. So that explains how we drew this df. Okay, and we know what is the value of df. And I'm going to, if I have to write it as a vector, I will give this r cap as the direction. Okay, now we have to use symmetry. How do we use symmetry? Or before using symmetry, if I want to know the total force on Q naught, what should I do? I should take such elements from every part, starting from minus L by 2 to plus L by 2. I have to keep taking these elements and draw R for each of them and find the net force. But if I do that, what will happen is, if I take an element here and draw my R vector, F direction is going to be different, DF direction is going to be different. Or for every charge element, DF direction is going to be different. So how do you actually integrate vectors which are all having different directions? It becomes very difficult. You cannot add. So this is where you have to use the concept of symmetry. So how do you do that? What you need to do is take a mirror element here. Take a mirror element here at a distance z in the minus z axis. Okay, at a distance z, take a mirror element carrying a charge dq having a length dz. And then for this element, get, okay, again, you will see that it is at a distance r only. And if I draw what is my df vector is again going to be repulsive. This is my df vector. Okay, or in other words, now I have taken two elements, a mirror element from the bottom, one element from the top, and I have drawn two df vectors, one df vector here and the other df vector here. And quite simply, you will be able to see that there is a symmetry in the picture. And if I say that theta is the angle that this r vector is making with dq, here also theta will be the angle that this r vector is going to make with dq. Okay, this line is also going to make an angle theta with the y-axis. This is also going to make an angle theta with the y-axis. And again, the distance r is the same, dq is the same. Therefore, you are actually going to add two vectors which are like this, having the same magnitude. Two vectors like this having the same magnitude. And how do you add them? If this angle is theta and if this angle is theta, automatically vertically opposite angles, this and this also will be theta. Okay. Now, how do you add them? How will you add them? Anyone? So, what you can see here is that I will use another color. Okay. So remember, this is my y-axis and this is my z-axis. I can resolve this vector into two components like this and like this. Similarly, I can resolve this bottom vector also into two components like this and like this. Okay. Now, what will these two be? Along the z-axis, what I have will be equal and opposite, and they will cancel out. But what is along the y-axis will be two parallel vectors. What is along the y-axis will be two parallel vectors. And you can see that you can construct a right angle triangle and you can show that this will be, okay, along the y-axis, what you get is going to be 2 times df cos theta. That's not difficult to understand. This is theta. Okay, so what will this be? This will be df cos theta, and this is my df. Okay, and similarly from the bottom also I'm going to get one, from top also I'm going to get one, so I get 2 df cos theta. I already know what is my df. Now without a vector symbol, let me just take my df. I will write 2k q naught lambda dz by z square plus r square. And now what do I write for my cos theta? What do I write for my cos theta? Now look at this right angle triangle. Look at this right angle triangle. This side is z, this is r, and this is y. So what will be cos theta? What will be cos theta? From the triangle, cos theta will be y by r. Cos theta will be y by r, or it will be y by under root of z square plus y square. Clear? Okay. Now I can simplify this. I can take this z square plus y square and under root of z square plus y square. I can simply call it as z square plus y square whole thing to the power of 3 by 2. Okay. I finally got my net force because of these two elements, and I find that the net force is along the y-axis. Next, I want the total force. I want the total force. What do I do? What should I do if I want the total force? Integrate. I have to do an integration. So df is going to be equal to integral df. So let's first integrate. And I'm putting a y cap now here as the direction, because I know that the direction of the two df's resultant was along the y direction. So if I take all such mirror elements from the top and bottom, okay, and keep adding, all such vectors will be along the y direction. So all I need to do is just do an integration. So I just write everything, and I have to do an integration from minus L by 2. So yeah, this is my element, minus L by 2 to plus L by 2. This is my origin. I have taken one element here, another element here. Similarly, if I have to do all elements, what should I do? I should take all elements from 0 to plus L by 2 and multiply by 2. Take it from 0 to plus L by 2 and multiply by 2. It is the same as taking from minus L by 2 to plus L by 2. Okay, so I have to just do a different integration from 0 to L by 2, but multiply by 2. Okay, so look at this. So I put everything into this, and I can see that all these becomes constant. Lambda is a constant, y is a constant. Y is a constant because my charge q naught is here and this distance is y. It's a constant. Okay, so y is also a constant. There is only one variable here. Which is that variable? Which is that variable?
Z.
Z. Only Z is a variable. So everything else comes out of the integration, and the formula is integral dz by z square plus y square to the power of 3 by 2. The answer is z by y square under root of z square plus y square. This you can take from the table. Integration table you can use and get it. Or if you have patience, you can actually arrive at this answer. Okay. Next, what is done is substitute the limits. When you substitute the limit 0 to L by 2, what happens? Let us see. Straight away, you can see that for the lower limit, this is going to be 0 because Z is on the numerator. And for the denominator, just substitute, for L by 2, just substitute upper limit, substitute L by 2. So wherever Z is there, put L by 2. And for the lower limit, Z is 0. Therefore, that part goes off. So when you substitute, you are going to get this as the answer. Or you can now conclude that because of this kind of positive uniform line charge distribution, the net force on Q naught will be the force F along the y direction. It's a repulsive force. Any doubts? Any doubts? Okay, there are no doubts. I'll just go ahead. Okay, next. What we got, we have to see whether it is dimensionally all right. Whether it is dimensionally all right, we have to see. Okay, so how do I test whether it is dimensionally all right? K is okay, 1 by 4 pi epsilon naught. Q naught is a charge. What is lambda into L? What is lambda into L?
Q.
Q. Yeah, that's also all right. And denominator, I should get square of the distance. So I'm getting y here. And dimensionally, if you see what is under root of this also is going to be meter. Y is also meter, so I get meter square. So I should, when I get a formula like this, I should see whether it is consistent with the dimensions of Newton force. Okay. Next, another thing that I should do is, what happens if y becomes much greater than L? What happens if this distance y becomes much greater than the total length of the charge distribution? I'm taking a point far away. Okay, so how do I do that? So quite simply, one can do this here. So I can write F will be equal to K Q naught lambda. Okay, or I will do one thing. I will write lambda into L as Q. And now come to the denominator. I have my Y. And what will happen to this term? What will happen to this term if Y becomes much greater than L? If Y becomes much greater than L, then L square becomes much more negligible, right? L square becomes negligible. So you can drop this term and you will simply have under root of y square. What is under root of y square? Under root of y square is y. So y into y, you will get y square. So what is this equation? Anyone can tell me?
Force between 2-point charges.
Yes, force between 2-point charges Q and Q naught. Right. So this is the force between 2-point charges Q and Q naught. That's okay. Logically, that is fine. I have a line charge here. If I'm talking about a charge Q naught which is close, it will be able to see this as a line charge. But if my point is far away, it is not going to see this as a line charge. It's going to see it as a point charge. So I'm able to get an expression for 2-point charges. So that means my formula is right. Whatever I have derived is right. Okay, next question. What if my rod is negatively charged? What will change if my rod is negatively charged? My rod is negatively charged. Then what will be the direction of DF?
Towards the
Right. You would have got a DF like this and you would have got a DF like this. So the net force would be in this direction. So it will be a attractive force. Again, along the y-axis, but it is attractive. Okay, next question. What if L becomes infinitely large? What if L becomes infinitely large? Then how will this formula change? Anyone?
Y becomes
I can be neglected.
I'll insert a new slide. Okay. So let me just see. I'll try to answer this question. What if L is infinitely large? So what do you do? Where will the derivation change? Where will the problem change? At which stage will it change? So what happens is F will be equal to, if you remember, 2k q naught, then we had lambda, then you had y, then you had, then after that you did an integration of dz divided by z square plus y square to the power of 3 by 2. So what do you think will change when the line is infinitely large? When it was not large, it was 0 to L by 2. Now what will happen to the limits? Limits will become 0 to
Infinity.
infinity. The limit will simply become 0 to infinity. Okay, so you can just do it. Okay, once more it's going to be the same way. You have to do 2k q naught lambda y, and then let me write the answer. Okay, nothing. I am just taking it from the previous slide only. Z divided by y square into z square plus y square to the power of half, and then I substitute the limit 0 to infinity. So 1y goes from the denominator. Okay. Okay. Now what happens if I put? So if I put the lower limit is going to give you 0 only. So the upper limit. Let us see what happens. Q naught lambda z divided by y into, let me just take z tends to infinity, so let me take z out of this under root. So I get z into 1 plus y square by z square to the power of half, right? I've simply taken the z square outside. When I take z square out of this under root, what will I get? It becomes z, right? And it becomes 1 plus y square by z square. And now substitute the limit 0 to infinity. This z and this z will go. Okay, so now what will happen? What will happen? Anyone? Hey, you are all mathematics students, yeah? Q naught lambda by y, I write here. And what will happen to this when z tends to infinity? Hey, am I asking you a difficult question? When z tends to infinity, what will happen to y square by z square?
0.
0. So I will have only 1. Right? I will have only 1. So this is going to be the answer for the force. Or if I write again, I will get K, I will write it as 1 by 4 pi epsilon naught. So I will get 1 by 2 pi epsilon naught into Q naught lambda by y. This will be the answer. Okay? So these kind of things can be asked in an examination. You know how to do it for L, so do it for infinity. Okay, now let's move to, this is again going to be a line charge, but it is not going to be a straight line. It's going to be a ring of charge, a uniform ring of charge. And let the ring have, and please remember we are talking of insulators. That line charge also was an insulator. Charge is not moving. It is electrostatics. Okay, so here also we have an insulating ring carrying a total charge Q. Okay, let me just write the total charge as Q. And then the radius of the ring is R. The charge is uniformly distributed. So what is the first thing you will do? You will write your charge distribution. Total charge divided by the length. Why did I write 2 pi r here? Charge divided by 2 pi r. Why did I put 2 pi r?
circumference of the circle.
Yeah. So that's the length. The length of a circle is 2 pi r. Circumference. Okay. So lambda equal to q by 2 pi r. Next, what do? You have to take, as usual, take a small length element. Okay. Only thing is because now it's two-dimensional, I will not call it dx and all that. I will call it dl. Let the length of this element be dl and let it carry a charge dq. And and I want to find out what is going to happen to q naught because of this element. Let the force be df. The force is df because it is a repulsive force. And this dq is at a distance small r from q naught. Okay. Next, what do I do? I have to write my dq in terms of lambda. So I will write dq is equal to lambda into dl because the length of the element was dl. And I can also do one thing here. I can call it as dl is an arc length, right? dl is an arc length. So let us say that this arc is going to subtend an angle d phi at the center. It is subtending an angle d phi at the center and capital R is the radius. So how do I write dl then in terms of R and d phi?
R D phi.
Right, I can write dl as R d phi. Yes, I've done that. Okay, now let me write the equation for df. df is k into q naught into the other element is other charge is dq divided by r square. Direction is r cap. Next, instead of dq, I am just putting lambda into dl or lambda into r d phi. Fine. Next, what do I do? I find that if I want the net force, I should take all elements. I should come around the circle once, taking all such elements and all such df. But I will find that each of this df is going to have a different direction. Now, how do I add them? How do I do the integration? So again, go for symmetry. So what do? You have to take a mirror charge element here. Exactly, diametrically opposite. Take an element dq of length dl, okay, identical. And then talk about what is going to be the force because of this element at q naught. You will get an arrow like this. This will be df. Okay, and where are my elements with respect to my q naught? I will call this angle as theta. I will call this angle also as theta. Both will be theta from symmetry. Or now what I am having is I am having two vectors like this, df, another vector df, both having the same length, and I know that this is my z-axis, okay, and I have to now add up these two. Okay, and I know that these two angles are theta, therefore this angle also will be theta, this angle also will be theta. Okay, so can someone tell what will be the components? Which component will cancel out? I can draw the components for this vector as this, and the vertical component is this. Similarly for this one, it is this and this. So the horizontal components will be equal and opposite, they cancel out. They cancel out. So only the z components will survive. Only the z components will survive. Okay. So what will it be? It will be 2df. 2df. You see what if I have a triangle like this? What will this red arrow be? Cos theta or sin theta?
Cos.
Cos. Therefore df cos theta. Again, do what I did previously. Take this right angle triangle and get your cos theta. What will be cos theta? Cos theta.
Z by R.
Yeah, it will be z by small r. Z by small r. Or I can write it as z by small r can be written as under root of r square plus z square. Capital R square plus z square. Capital R is the radius. So now I'm going to put this into this equation. Okay, and then substitute for df. And I get this. Okay, now what we will do is, we will look at what are all going to be inside the integration when I integrate and what all will come out. Can someone guess? For the net force, I'm going to integrate this. What all will come out of the integral? Can you guess? Before I show it, I want you to tell me. Which are all constants? Is Q not a constant?
Yes.
Yes, ma'am.
Lambda,
Yes.
R, capital R,
Yes.
Z.
No.
Why? I fixed my Q naught position, no? I knew you'll answer this way, that's why I asked this question. I fixed my Q naught with respect to the Z axis. I take this as my origin. So Z is also a constant. So then what is the variable?
D phi.
D phi is the variable. So you are going to just do integration over D phi. And if I have to take all elements once, what should I do? I can start from here and take all elements till I reach here. At the same time, I'll be taking all elements like this till I reach here. So if I just go around that circle, half a circle, and multiply by 2, I would have covered the entire circle. If I go half a circle once, then it is as good as doing it because 2 times I'm multiplying. So it's as good as coming around the circle once. Okay, so that's what we'll do here. So the net force on Q naught is going to be just the integration. So therefore, it is integrating from 0 to pi. That is only half a circle we integrate because 2 is already incorporated and the component is already taken. And what will be 0 to pi d phi? Just pi. Just pi. Very simple. All other terms remain as it is and you get this. And here the only thing I have done is, what will be lambda into 2 pi r?
Q.
Q. That's it. And then once more, I can check dimensionally whether this is okay, whether it has got the unit of force. Okay, now tell me, I have my ring. Once more, I'm back to the same question. I have my ring. I have my Q naught here at a distance Z. What if Z becomes much, much greater than R? Will Q naught see this as a ring? Q naught will not be able to see it as a ring, see it as a point charge. You see it as a point charge. That is what you will get here when you try in this equation, when you try to make Z much, much greater than R. So R square will just get cancelled out. You can just neglect it. Okay, and there is a Z cube at the denominator, Z at the numerator. Therefore, I'll get Fz is equal to K Q naught Q by Z square. So that means I am fine. My equation that I got is right. Next, what if the ring is negatively charged?
Force will be towards negative Z.
Negative Z. In this case, it is a repulsive force. Here it is a repulsive force because both are positive. But if one were to be negative, then there will be an attractive force. Okay, there is a third question. What if my Z becomes 0? What is the meaning of saying Z becoming 0? Z becoming 0 means I'm going to put my Q naught here at the center. Then what will be the force?
All forces would cancel each other.
If I put my Q naught bang at the center of the circle and make my Z 0.
They all would
What will
cancel
be
each other.
I don't know, I'm not able to hear you. Can you speak slowly? Can you speak slowly and tell me? You look at this expression, tell me now what will happen when Z becomes 0. The answer will be, oh, the thing is your chat, I'm not able to see. This is sitting on top of it. So maybe somebody is answering there. It becomes 0. That's right. It becomes 0. That's right. Good. So the force will become 0. That comes even from the equations. And these are all actually checks. These are all actually your checks, whether you are doing it in the right way. So I'm able to see that when I put it at the center, I'm going to get 0. That means my answer is right. Okay, now there is another question. This is an interesting question. I know that the force here will be 0 when I put Q naught at the center. What will be the force when Z tends to infinity? When Z tends to infinity, what will be the answer? Anyone? Just answer. I'm not able to see your chat. It is embedded in the layer behind. It need not be the same people answering. Please take turns and answer. What happens if Z tends to infinity? If I have a charge Q0 here and another charge at infinity, will these two talk to each other? They will not interact. Therefore, the force will be 0 at infinity. If the separation is infinity, the force will be 0. Force is 0 here also. So that means I'm having 2 points where the force is 0. One at z equal to 0, other when z tends to infinity. So somewhere between them, there is a point where this force is a maximum. Did you understand my logic, guys? At z equal to 0, it's 0. At infinity, it is 0. So somewhere between these two, there is a point where the force is a maximum. Can you locate that point? Can you locate that point? How will you locate that point? Anyone? So this is the equation for the force. Okay. I want to find out what is the value of z where this force is going to be a maxima. I've already given the answer.
Differentiate with respect to Z.
Beautiful. So now just use your calculus and then differentiate this with respect to z. So now z is not z is not a constant. Z has become a variable because I am able to move my q0 and I have to find out some location for z where the force becomes a maxima. So this force will be a maxima when the first differential is equal to 0. Can you just try this, guys? Anyone? Try this. And then equate it to 0. So we can do one thing. We can just leave out this fellow. Because after all, this is sufficient. All these are constants. So leave them out. Just do the differentiation of this. So what will I get? I will get 1 by z square plus r square to the power of 3 by 2. Then what will I get? Plus z into minus 3 by, I'm taking the denominator here and I'm going to differentiate, minus 3 by 2 into z square plus r square to the power of minus 5 by 2 into differential of z square, that is 2z equal to 0. Okay, or I can write it as 1 by z square plus r square to the power of 3 by 2 minus this 2 and 2 will cancel out. Okay, therefore I can write it as 3 minus 3z square divided by z square plus r square to the power of 5 by 2 equal to 0. Okay, so from here what will I get? 1 is going to be equal to 3 times z square divided by z square plus r square. That is, here is a 3 by 2, here is a power 5 by 2, so 3 by 2 can go and then leave me only with z square plus r square. Okay, then do the cross multiplication. So I will get z square plus r square equal to 3z square, or I am going to get, I will take the z square this side, so 2z square is going to be equal to r square, or I will get z equal to plus or minus r by 2. Is it clear?
Yes.
Right. So what do you conclude? At z equal to plus minus r by root 2, f is a maxima. Why this minus? What is the significance of minus? What is the significance of minus?
Negative Z axis.
Right, negative z axis. So whether I take it here or I take it here, at that distance r by root 2, I'm going to get maxima. Okay. So I don't know whether you are realizing it. As we are discussing, we are also parallelly working out problems. These are all numericals actually. We are working out numericals as we discuss. So in the next class, what I want to do is just try this, guys. Just try this. Note down this problem. Instead of a full circle, I'm going to have a semicircle. I'm going to have a semicircle, uniform charge distribution. I'm going to put a point charge Q naught here at the center. Radius is R. Okay. Now, let the total charge on the semicircle be Q. Can you find out what will be the force on Q naught and what will be the direction of the force? Assume Q naught and Q are positive. Note it down. Please note down this problem because it's time up. I'm going to stop the class. Okay, try this problem and come. You will have to use polar coordinates to solve this problem. Just try it. Okay, any doubts on what we have studied today?
No, ma'am.
Okay, anybody? Are you comfortable with, because I don't know, many of you could be sitting there who have never been taught by me. Are you comfortable? If you have any difficulty in understanding the class, please put it in the WhatsApp group. Because you get taught by one faculty, change of faculty, both of us are good in our own ways. But then, you know, that getting used to another faculty can take time. You can always put your comments in the WhatsApp group of section 1. Okay, so I'm going to stop sharing now and let's call it off for the day. And today there is a lab hour. Please come for the lab. For a few minutes, you have to attend lab. Okay?
Thank you, ma'am.
Yeah, you can leave.